Okay, so quickly before the lecture, I just want to show you on the in the Canvas. So I've, based on your selection of the paper, so and the date, so I've kind of list the schedule here for the paper presentation starting on March 1st. So you guys can see the schedule, and you can check when is your date for the presentation, and you can start to prepare these slides. Okay, so you want to leave you enough time to kind of understand the paper and well prepared for the presentation. Okay. Okay, so for today's class, we'll talk about generative adversarial networks, so which is short for GANs. I'm sure some of you already heard of GANs, right? So it's very popular, has a lot of applications. So for today's class, we'll talk about GAN. So this is the paper for the generative adversarial networks, and this was authored by Ian Goodfellow, some other co-authors, and this Joshua Bengio is his advisor. He's also the winner of the Turing Award. Okay, so if you look at how many citations it got so far, right, since the publication of 2014 in Europe, we got 40,817 citations. So, which is really a lot of citations in the field of AI or machine learning. And you can also kind of see a reflection how popular these generative adversarial networks soon become when this paper published. So based on the name, right, generative adversarial networks, so we can basically, there's like three concepts here, right? So first of all, the generative. So for the GANs, it is a generative model, which means it is able to kind of approximate some of the data distributions. Okay, so if the model is able to approximate these distributions, then we can using this model to generate new data point. Okay, so that's the generative model. So the goal is to generate some of the new data, right? So you see a lot of computer vision based applications, right? So the GANs is used for data, image, or video generation. And this adversarial term means there's going to be two competitors. Okay, so for the GANs, for the computer vision task, later we'll talk about these two competitors. One is called the generator, and the other is the discriminator. Okay, so these two players basically competing with each other. Okay, the generator trying to generate realistic fake data, right? Looks more like a real image, and the discriminator is trying to improve its ability, trying to distinguish if this is a real data or it's a fake data generated by the generator. Okay. And for the networks, mostly we're using the deep convolutional neural network, and also can using some of the dense network, right? These fully connected neural networks. And GAN is very popular, right? So let's look at a couple of very representative applications, right? And see why the GAN is gaining so much hype or interest in the research field. So the first application is data generation, right? We can generate a lot of unseen data, right? So here, this is used to generate facial images, right? We can, for input, then it is able to generate other facial images, right? Maybe adding the glasses, right? Removing the smile or adding the smile, right? So this can be considered as an effective way for the data augmentation, right? If you have a limited data for the training and you want to do some data augmentation, right? So of course you can using the some of the common or typical data augmentation like rotation, cropping, translation, etc. But GAN is also a very good approach that you can generate some of the images that contain some of the additional information, right? Like adding the glass. And on the right side, you can also see not just for the facial images, the GANs can also generate any type of natural images, right? Like these cat, dogs, this cute mouse, etc. And GANs also being used in image-to-image translation, right? In not just randomly generate some of the images, but you can, based on an input, and generate the desired output, right? So image-to-image translation. For example, giving input, which is a semantic segmentation map, right? So these different colors indicating different classes, right? Which we talk about from last lecture, right? Semantic segmentation. And it can generate the output will be the natural image, right? Which has the corresponding segmentation map, right? So here, if you see there's a car, right, or maybe a van, right, will generate this kind of image or object, right? This is the road and this is the tree, right? Will generate these objects that are corresponding to the semantic labels. Okay, so here another example, right? So if we are given aerial image, it can generate the corresponding output as the map, right? So as you do the navigation, we can generate this map. And we can also do day to night mapping, right? The same image, but I want to generate image that as if this scene was taken at the nighttime, right? And also image coloring, right? You have a grayscale image, then we can generate this corresponding color output. And here's another example, right? We can generate the emojis, right, from the original photo. And GANs can also be used, to generate images based on the text, right? So not just from maybe some of the random noise you generate image, but we want to generate some of the image has some meaningful information, right? That is, contains some of the semantic information that resides in the input text or sentence, right? So for example, this particular example, right? So this magnificent fellow is almost all black with a red crest and white cheek patch, right? So obviously there's a couple of very important attribute or semantic information in this sentence, right? Describe the object, right? Which is, the body all black, right? With a red crest and a white cheek patch, right? So you can see how GAN is able to generate image fit this kind of description, right? This is all black, right? We have a red crest here. And also you can see there's some white, cheek patch right here. Okay, so it's able to understand some of the semantic information or attribute for the input and generate an image, match that kind of description. Okay. Yeah, so those images are, fake image, right? Those persons are not exist. So you're right. So we'll talk about a little bit more on those kind of issue. Some of the negative impact essentially later. Okay. Okay. And GAN also can be used for photograph editing, right? So if you're using Photoshop, so I think Adobe, they incorporate some of the advanced technique that based on GANs, for the photo editing, right? So you can using this real image input, and then maybe, generate different hairstyle, right? Become a blonde, right? You can adding smiles, etc., right? And also another application would be, I think it's just very important, is maybe for forensic, right? So, the police may trying to, find some suspect, right? You can some artists can draw an image, right, based on the description of the witness, right, what this person looks like, right? We have a sketch or drawing, right? The artist can render this kind of drawing, then this scan is able to generate maybe realistic kind of human portrait, this photo. So this can maybe very helpful, for the police to solve some of the crimes. Okay. And also photo blending, right? So here is one image and this is another image, totally different scenes, but maybe we want to combine these two or take some of the information from this image, right, and put that into another image, right? For example, this is their like a green field, right? We want to put it lay on top of another image, which you can make it more realistic, right? There's no like artifacts when you do this kind of blending. The next application is the image recovery or image enhancement, right? So on the left, you will see this is called image super resolution, right? So basically, you have a very low resolution input, right? So you can see, these very low resolution, right? Kind of blow up to the same size, then you couldn't see much of the detail of the person, right? And then we can using GAN. So this particular method is called Pulse, which is using the generative model. And you can see the output is this very high resolution image, right? Compared to the input, this is the output, right? You can definitely see there's a lot of details has been generated or enriched by this approach. Again, this is very important, like for the surveillance or forensic, right? I'm sure you guys watch some of the movies or like a CSI TV shows, right? Oftentimes you will see they have a surveillance footage, right? And they have like a suspect, then they crop a small region of that face, right? Maybe the footage captured like hundreds yards away, right? The detail is very small, right? Just low resolution input. Then magically, the boss says, okay, enhance that image, right? So they were able to generate this kind of very high resolution output, right? So actually we can do that right now, right? Based on this one. So you have this low resolution, we're able to generate such high resolution image. And on the right side, this is the also image enhancement, right? So on the left, you may have some old photos, right? Maybe some like your great grandfather, grandmother, right? At that time, they do not have like this color cameras, right? They only take this kind of black and white photos, and the quality of the camera may not very high. You also have a lot of noise, right? So now we can using this kind of technique to enhance the photo, right? To generate high resolution. At the same time, we can do the coloring, right? So as you can see that, this is more, you couldn't tell this is like a computer enhanced image, right? You wouldn't think this is like actual photo, like maybe taken recently, right? Very high resolution, very vivid color, etc. Right? So these are the other two images generated by this GFP GAN. Okay, so and we can also actually there are some some of the like video platforms, they are also using this kind of GAN technique to produce 4K videos or movies, right? The old time we don't have color cameras, right? So we have some of those kind of black and white movies, and we can apply this kind of technique to enhance the resolution at the same time, give the frame color, right? So we can kind of see more details and for those kind of old movies, okay? And of course, the GANs can be applied to video applications, right? So we can do video frame predictions. And based on the current, maybe a couple of frames, then we can predict the future frames, right? Maybe 10 or even more frames in the future. Okay. So one application could be, again, video enhancement, right? If you have a video which is low frame rate, right, maybe 10 frames per second, then you can using GAN to interpolate those intermediate frames, right, to increase the frame rate to 30 frames per second, right? So that's another, that's a one, example application for video prediction. And also for the application like autonomous driving, right? So we can using GAN to predict the future frames, right? So for this particular example, right? So this person is working behind the car right here, right? It's kind of occluded, right? So if we are able to predict the future frame, maybe the next 2 or 3 seconds, right? What would be the trajectory of this person, right? And this will give this autonomous driving system maybe more information to make the correct decision, right? Should the vehicle, hit the brake, stop early, right? To prevent like hitting this pedestrian, okay. Okay, of course, GANs can be used in medical imaging domain as well, right? So a lot of applications, share some similarity, right? The segmentation, image reconstruction, etc. Right? So we can using GANs to, for this medical imaging task as well, right? So this MRI reconstruction, and we have brain disease detection or segmentation, also these CT denoising, right, to enhance the quality of the CT image, so you can doctors can make better diagnosis, right, and also data generation, right. So maybe we don't have this CT modality for this particular patient, but we can using GANs to synthesize the corresponding CT scans. So together with the MRI CT modalities, maybe can make better diagnosis or treatment plans for the patient. And of course, we can do image generation as well, right? So if some of the disease, maybe you don't have enough samples, right? Rare disease, you cannot collect a lot of data samples, then we can use GANs to generate synthetic data to help you to train the machine learning model. Okay. So the high-level overview of the GAN is, you want the generator, right, taking some of the random noise, and it is able to generate output that is sampled for a specific distribution, right? So you want a mapping to a approximate specific distribution, for example, the realistic or natural image of your some of the training data set. So to train the GANs, right, it is involved this two-player game, right? You have this generator, and you also have the discriminator, right? So these two players in the GAN training. So the generator, the goal is to fool the discriminator by generating realistic, looking images, right? So you can consider, for a particular example, that the generator could be like art forger, right? So you want to generate art paintings, like maybe produced by some of famous artists, right? And the discriminator network then is trying to distinguish between the real and the fake image, right? So in this particular example, discriminator can be like FBI agent, right? Trying to tell if this painting is the art or maybe some forgery, okay? So for the generator, it takes the noise, right, and go through some of the network, right? Can be deep convolutional neural network. Then it will output some of the generated fake images, okay? So for the discriminator, it takes the fake image generated by the generator. It also takes some of the real image, right, from the training set, right? Because the goal is trying to teach or train the discriminator to tell what image is real and what image is fake, right? We feed some of the real images from the training set and to this discriminator network. Again, this can be, deep convolutional neural network. And the job of the discriminator is doing some binary classification, right? Is this input a real image or fake image? Okay. So typically we're using G to indicating this is generator, and D is indicating this is discriminator. Okay. And to train this GAN, we'll have this joint training in this min max gain formulation, right? So this minimax objective function, you have minimization, you also have a maximization, right? So here the D, theta D is the discriminator network parameters, and theta G is the generator network parameters, okay? So D is the discriminator and G is the generator, okay? And this is the output probability of the discriminator. And we'll talk about the detail, these two terms in detail. So the discriminator outputs the likelihood in the 0-1 range of the image, right? 1 indicating this is a real image and 0 indicating this is a fake image, okay? So this is the discriminator output. If we look at discriminator first, okay, let's just just consider this discriminator for this second, right? We forget about the generator, right? So now for this objective function, right, we only consider the discriminator. So it has the want to maximize, and let's see what terms is trying to maximize. Here we have the D here, right? In the first term, we have the discriminator, and also we have the discriminator in the second term, right? So this is the discriminator output of the real image from X, okay? And this is the discriminator output for the generated fake data, GZ, right? Z is the random noise and GZ is the generated image. So this is the likelihood, right? From discriminator, is this a real image or it's a fake image, okay? So why the discriminator wants to maximize these objective? So let's look at these two terms, right? Let's say, because this is a real data, right? Real image X, right? So you want the discriminator to give you output, right? As close to 1 as possible, right? So it means it is able to distinguish, this is a real data, right? Because output a probability of 1, indicating this is a real image, right? Let's look at the second term, right? So for real, for good discriminator, it also has to, able to kind of distinguish this is, or tell this is fake data, right? So that means the GZ should be close to 0, right? 0 means that's a fake data, okay? So if we go from here, right, we look at these, the curve of the log function here, right? So if this one output as a 0, right? So 1 minus 0 is, so that's 1, right? So actually that's the maximum you can get here. So that's why if you're trying to maximize these two terms, right, you will trying to push or make this discriminator to output a probability of this GZ to 0, right? So that's exactly what we want for this discriminator to do a good job, right? To maximize the DX such that it close to 1, right? It is a real image, and also make the GZ close to 0. So that's a fake image, okay? So is this clear? Any questions? Okay. So next, then let's look at the generator, right? So we understand the objective of the discriminator. Then what about the generator? Okay. So if we look at the generator, right? So here this theta G is the parameters of the generator network, right? It's trying to minimize the term. So here we don't have any term related to generators, right? So we only look at the second term here. So remember the goal or the objective of the generator is trying to generate a fake image that is look as much as possible like the real image, right? So it will try to fool this discriminator, right? This is a real image, means DGZ should be close to 1, right? Fool this discriminator, think, okay, the generated image is a real, it's a real image, right? You has a likelihood or probability equal to 1. Okay, so if we minimize this term, right? So if you want to minimize, which means this log 1 minus this term should close to 0, right? So we trying to minimize that. So in this case, then this d theta gz should, close to 1, right? So it makes this 1 minus term become 0. So that means, the discriminator think the generated image is a real image, but actually this is the fake image generated by the generator. Then, generator kind of achieve its goal, okay? So now we understand these, the objectives for this generator and the discriminator. So then we put it together, and to do the training, we're gonna alternating the optimization between this generator and discriminator, okay? So we first will do the gradient ascent on the discriminator, right? The reason we're using gradient ascent, not descent, is because we are doing the maximization, right? When we do the minimization, we're using gradient descent. So here, because of the maximization, we're using ascent. Okay, of course, you can add a minus sign here and using gradient descent. And the second step, we'll do the gradient descent on the generator, right? Because we'll minimize this loss function. And in practice, people find we can change or modify this objective a little bit, right? Instead of minimization, can also do maximize these instead of 1 minus, just the GZ. And this, in practice, makes the GAN training more stable. So that's the kind of one good practice for training the GAN. So here is kind of like a summary in terms of pseudocode, right? How GAN is being trained, right? So we can specify a couple of training iterations, right? So actually we have 2 loops, right? We have a large outer loop, then we also have an inner loop because we alternating the training process for these 2 players, right? So for the inner loop, for the case steps, we sample a mini batch of M noisy samples, right? This is for the generator to generate some of the images, and we also sample some of the examples for the training data, right? The real image. And with these 2 data, we update the discriminator, right, by gradient ascent. And after a couple of case step it finished, then we now optimize the generator, right? We sample a mini batch of M noise and update the generator by gradient ascent. Right here, we are also maximized instead of this log 1 minus here. And a small note here is some people find how the k equals to 1, right? Just do 1 step seems to stabilize the GAN training, but others may using greater than 1, right? You can using 5 steps, but there's no like rules to set these values. So it's kind of depending on your application, and you can tune to the based on your application, and have the best k steps for your training. Also, some of the following work, like a Washington GAN, also kind of alleviate this problem, better stability. So if you're interested, you can check these reference. So after the network training, right? So then during the testing phase, right? The goal is to want to generate data, right? So we're just using the generator to generate the new image, right? So once the network is trained, then we are kind of pretty confident, the generator is able to generate some of the realistic image. So we're just using that to generate the data. Okay, so here I list a couple of resources, right? You kind of walk through, if you want to implement the GANs, then how you can implement step by step, and also some of the training tips, kind of to stabilize the GAN training. Usually GAN is very difficult to train because you have these two networks, you alternating the optimization. So you need some of the good practice to stabilize the GAN training. So highly recommend you read these kind of tips, and they could be very helpful when you actually implement or train your own network. Okay, so next we'll talk about a variant called the conditional GAN, right? So in the conditional GAN or CGAN, the generator learns to generate a fake sample with a specific condition or a characteristics. For example, you have a label, right? It's not just randomly generate some of the image, but you actually have some target, right? You have some condition. Maybe you want to feed the network a label, right? This is a cat, right? I don't want you generate any arbitrary image, but generate an image that is a cat, right? Or image containing a cat, right? So that's some of the some of the label information. And we'll talk about one particular pipeline called pixel to pix, right? Image to image translation that are using conditional GANs to achieve this task. Okay, so here this is the task this pix to pix framework is able to achieve, right? So so input this semantic segmentation map, right? That's kind of like a condition, right? So have this condition, right? I have this semantic segmentation, generate an image corresponding to this semantic segmentation map, right? So another application, they want to map area to image to map, right? Giving you this input as a condition, generate output corresponding to this kind of input, okay? So this one is the unconditional GAN, right? Just the vanilla GAN we just talked about, right? You for a random noise, right? You take that as input to the generator and generate some image, and this will go through the discriminator and tell if this is real or fake, right? So here, let's say I have a edge image, or maybe this is a sketch, right? If I using this kind of unconditional GAN, right, I may generate image like this, right, this bag, and the discriminator may tell you, okay, this is a real image, right? You did a very good job. This looks realistic, okay? And it is also possible, right, the generator generate this image, right? And if we feed this image to this discriminator, it'll also tell you this is a realistic image, right? This is also a handbag realistic image. But for our particular application, right, we do image to image translation, right? The ideal case will be have this input, right? And we want to generate this kind of output, right? So this edge exactly correspond to this particular realistic photo, right? We don't change the geometry or the shape, right? But the unconditional GAN, right? Because you're not, kind of enforce the network corresponding to this input, may generate image like this, right? But in this case, this is not the ideal one. So in order to achieve this kind of image to image translation, so this pix to pix framework, they using the conditional GAN, right? So once you generate this image, then I was using this input, right, X, together with the general image go to the discriminator. So now instead of a single image, now we have a pair of image, right? And the discriminator will, based on the pair of image, and tell if this is a real pair or a fake pair, right? So if you generate image like this and you pair with this input, then most likely the discriminator will tell you this is a fake pair, right? Because there's some, shape geometry doesn't match with each other. Okay. So here the object function here, right? So we'll have generate image and input, and so y here is, you can consider that's a label information, right? So that's like a target image, right? Like the ground truth, right? During the training, you have a matched pair, right? So that's the y is indicating that's the target, right? So you have this real pair and the fake pair. So that's the optimization. So basically, it will match the joint distribution, right, for the input and its corresponding target, the label. And also, the generator is not only, trying to fold the discriminator, right, generate a realistic image. So the discriminator wouldn't tell it's real or fake. At the same time, it will try to generate image that is close to the ground truth, right? So in this kind of Euclidean space, right, we can measure how close is the general image as compared to the target. So in their paper, they also using this L1 norm, which is basically the mean absolute error, right, for the generated image and the target y. Okay, so this is trying to enforce the generated image as close to the target y. Okay, so together they have the gain objective and this plus these L1 norm term together for the final objective. And the once the network is trained, here are some of the examples they're able to generate, right? So given the input as the edge, and generate the corresponding images which match this kind of edge map, right? So this is the outcome, and as you can see that, right, the does match this kind of edge map, right? If you maybe apply the edge detector on the general images, you will more likely will get this kind of edge map, right? So here is the same. Maybe color can be different, but some of the shapes, right, will kept intact with corresponding to the input edge. Also can do the sketch to image, right? This is maybe some of the hand sketch, hand drawing as the input, then generate the corresponding output. Okay, so I think here, as you can immediately think, there's have a lot of applications, right? Maybe if you are some artist, right, you are a designer, right? You can do this kind of sketch, right? Maybe draw, your favorite, sneakers, right? Then, you can use GAN to generate the realistic rendering of your sketch, right? Maybe you have different, actually this GAN is able to maybe generate different styles, right? The shape can be the same, but like the color combination and, some other things can be, very different, which may beyond your expectation. So that's very neat for this kind of application. Okay, so the author, they also have this kind of demo site. So if you're interested, you can go through this site and maybe, try draw something yourself, right? Very interesting. And you can, using this pipeline to generate the corresponding output, right? Okay, so here is another application they did, right? Not just from sketch or edge to the image, they also using the map as the input and trying to generate the output, right? This area view that will have this kind of map layout. Okay, so this is the ground truth. As you can see, it's not perfect, right, as compared to the ground truth, but some of the basic layout is kind of matched to this input, right? You have this kind of main road here somehow, and you also have another straight road here, right? You also have this kind of diagonal, maybe small road across the block, right? But some of the shape of the house definitely is not very good. Some are actually distorted and not cluttered together as you compare to the ground truth. But overall, the overall kind of layout is very close to the map input. And also image coloring, right? So have an input grayscale, then using this pipeline is able to color this image, right? So some of them are very nice, right? So these kind of understand this is a plate and have a different fruit, right? Ice cream, or maybe some I don't know, some dressing, etc. And also the butterfly, the flower, right? So look real, very realistic. Okay, so next we'll also talk about a very popular one and the kind of improved version over the pix-to-pix pipeline for image translation. So that's the unpaired image-to-image translation using cycle-consistent adversarial network, or cycle-GAN. So previously, for the pix-to-pix pipeline, right? So we kind of have a paired input, right? So at least for the training data, right? So we have this edge map, right? So we also have the target, right? This is the corresponding output, the desired output to train the model, right? This will be the condition. But in some of the other applications, this will pose challenge, right? Or limit its usability, right? It is because sometimes or for some applications, it's very expensive to collect the pairs, right? For example, if you want to generate such training data set, you may have to apply some edge detection algorithm, right, on some of the real images and generate these edge maps, right? Or if you don't want to using edge map, you want to using sketch, right? Maybe you have to recruit some of the artists, right, based on the real item of the image, then ask the artist to draw the corresponding sketch, etc. Right? And then for some of the applications, and having a paired image is just not possible. For example, here, if I have a horse image here, I want to are you able to find like a paired zebra image, right? So the same position, type of shape, but this is a zebra, right? It's not possible, right? And also here, there's if you want to do photo to painting, right? Is it possible to find the corresponding painting for every photos, right? It's not possible, right? And you cannot find like a painting corresponding to this exact photo input unless you hire some artist to paint enough example to train. But what we do is we do have is a large collection of paintings, right? But not necessarily corresponding to the photos or the scenes you have in your photo collection, right? But we do have different paintings. So that means this is unpaired, right? So for your X domain, you have the photo, but for the Y domain, you have the painting. It's so those are the two different domains, but they are not one-to-one correspondence. So the cycle consistent GAN is trying to solve this paired challenge. Come up with this kind of cycle consistent loss to achieve this goal. Okay, so for simplicity, then we'll just make a very easy or naive example, right? Let's just say my input is a horse, right? X domain is horse. Then I want to have an image translation to generate the corresponding zebra. Okay, so Y domain is zebra. So what they do is, for this cycle GAN is they actually have two generators now. Okay, so let's focus on this input. Okay, so you have an input X, which is horse. And let's say you have a zebra generator, G, okay? So G is mapping from X to Y, right? Horse to zebra. Okay. And so with this zebra generator, right? So you generate this kind of fake image, right? GX, right? And you also have this kind of discriminator, right? To tell if this is a real data or fake data. Okay, so then you also have another generator, which is F. Okay, F, you can say that's a horse generator. Okay, it is able to map a zebra to the horse domain. Okay. So now you can see there's a cycle, right? So you have a original have a input that's the horse, then you generate to the zebra, then you go back to the horse, right? So there's a connection, or the bridge is to these two generator, the zebra generator and the horse generator. Okay. And because we want to, the general image going to be corresponding to the original domain, right? So if we go back from the zebra to the horse, ideally these x hat should be, ideal case should be the same as x, right? If these G and F doing very good job, then x hat should be the same as x, right? So in this case, we can have a like a reconstruction loss or error, right? We measure the reconstructed horse image x hat, which is FGX, as compared to the original input, the original horse image x. Right here, again, we are using the L1 norm, measure the mean average absolute error. So the reason they're using L1 norm is they found the L2 introduced some of the blurring. So they're using the L1. So that's the the reconstruct loss or cycle consistent loss. And let's look at here, right? So if you have this red, these red box, right, indicating an input, this is horse. If you generate an image like this, right, zebra, and you go back to the original domain, right, you compare with the original input, right? So this is X, this is X hat, right? So you will see they're going to be incur a large cycle loss, right? The reconstruction error going to be large, right? Because the content is very different. Again, here for this example, right? If you generate this kind of zebra image and you go back to the host domain and you compare, you calculate the reconstruction error, again, you will have a large error, right? Only in this case, right? If you generate the zebra image is kind of corresponding to your input, then you go back to the original host domain, then you will have a very small reconstruction error. Okay. So, so on the right side, you will also see there's another cycle, right? So since we have these two generators, right? One is like a zebra generator, the other is the horse generator. We can also do another way around, right? So we have this zebra image. We first go through this F, the horse generator. Then we go using the zebra generator, go back to this zebra domain Y, right? We generate a Y hat. Again, we can have another cycle loss, right? So you have these two cycle losses. And here I show some of the output from this cycle again, right? So for the Monet's painting to photo, right? So the left is the painting, and on the right is the generate photo, right? So the style has been changed, but you can see the content kind of maps or matches the painting, right? And here's another one from painting to photo, and here on the right, this is the painting and generate the photo. Okay, of course, there is also some of the, can be considered as a failure case, right? So if you look at this is the original orange, although it is able to generate, kind of like an apple, right? You have this kind of, coloring changes or some of the texture change, but one thing to give away is for this region. Maybe this is not should be the region for may not be the actually correspond to the apple. And here's another example, right? So from orange to apple, okay. And here's some of the examples for horse to zebra. Here's another example, okay. And here's another failure case. So actually, kind of, for this person putting here will also generate this kind of zebra pattern. So, so this is one failure case. And we can do this for not just for a single image, right? We can actually apply this cycle again for every frame of a video. So you can generate this kind of translated videos, not just image, right? But obviously you can spot very obvious artifacts, right? Because of the motion. And you do this frame by frame, right? You missing some of the, kind of temporal consistency, right? Actually, you can see a lot of artifacts on this kind of a large motion part, right? The neck part of the horse or zebra, whatever. So that's something to think about, right? If we want to do this kind of video generation or translation, maybe this kind of temporal consistency can be also taken into account. Okay. So next we'll also talk about a couple of medical image applications using GAN. So the first example is the low dose CT denoising. As we discussed in the first lecture, right? So the computer tomography imaging, they're using ionized radiation, right? So for the medical diagnosis, of course, radiation, raise some of the safety concerns, right? So we want to reduce that radiation using very low dose to generate the CT. But accompanied with that is your image won't be very high quality, right? So you will generate some of the generate the image maybe with a lot of noise, okay? That will affect the diagnosis of some of the disease or pathology, okay? But we want to using GAN kind of denoise or enhance the image, right? So here on the left is the noisy CT input, and the outcome we want is a denoised, very clear CT image. So for this paper, they are using PIX-to-PIX pipeline, very close to similar to PIX-to-PIX pipeline, and apply this for CT denoising. Okay, so for the input to the generator, you have this low dose CT image, which is like a noisy CT image. And you go through this generator and you generate a virtual, this is conventional CT, which means you have a regular amount of dose of the radiation, so which has a very clear, crisp image, right? So let's consider this is conventional CT is the ground truth they targeted. So this is the generated, conventional CT image, right? So they using this pair of image, right? The virtual pair and the real pair go through the discriminator, to decide if this is a generated or the actual pair of, CT image, right? So here they also have the L1 loss, right? Is the generated or virtual conventional CT contain the same content, right? You don't want the content totally, different. So that's using the L1 norm, just like the PIX-to-PIX pipeline. Additionally, they have this sharpness loss, which they're using another network trying to detect the sharpness of the image, right? Because sometimes the edge or the sharpness of the image is very important to diagnosis of trying to discover some of the patterns, right? So they want to enforce that. So this just an additional loss. The second example is the MRI to CT synthesis, okay? So this paper, they using CycleGAN to achieve this goal, right? To from MRI to the CT scans. Okay, so because the CycleGAN, we have two cycles, right, from these two domains, right? Here we have MRI and a CT domain, right? So on the left, so the input is the MRI. They trying to synthesize the corresponding CT image, right? And you use a discriminator trying to distinguish or predict if this is a real CT scan or this is a generated CT scan. Okay. On the right side, it's another cycle, right? You have the input is a CT, and you can go through another generator, which is synthesize the MRI image. Then you can feed that into the discriminator, trying to distinguish if this is a real MRI or the generated MRI image. Okay. And here I'll show some of the examples of their generated or synthesized CT image. Right on the second, this is the generated or synthesized MRI. I mean the CT scans, and the third one is the ground truth. Okay, so they have like a pair for this particular patient. Okay, so that's the ground truth CT image. And the last one basically measure how, the reconstruction error or difference, right? So if you don't look at the differences, I would say the generated image are pretty close to the ground truth, right? So these kind of bone structure are very highlighted, right? So we know CT is good at capture the hard matter, like the bones, right? So the shape, everything is able to capture very correctly here. And the third example here is using GAN to do the organ segmentation in chest X-rays. Okay, so for their pipeline, it's just basically apply the GAN framework. Okay, so for the input is the chest X-ray. Okay, so for the generator, it's actually a segmentation network, right? So that's their generator. What this generator or segmentation network generate, it's the segmentation map they are generating. Okay, it's not like you are doing image generation, you are generate a natural image, but here, because they purposely make the generator a segmentation network, right? It will generate a predicted or segmentation map of different organs, right? Like the lungs, kidneys, or hearts. Okay. And of course, during the training, we'll also have the ground truth mask, right? Ground truth segmentation map, right? So this discriminator, and all they call it, this critic network, is going to differentiate, if this is a, the real generator, the segmentation map or the generated segmentation map. Okay. And the last example is the brain signal to image generation. Okay, so basically you will have a EEG signal, right? You have this EEG. You can wear it on one subject's head, right? This will measure these EEG signals, a multi-channel EEG signals, and you will using a GAN network trying to predict, right? What is the image this person is actually looking at, right? So that he or she will produce such EEG signal. Okay. So this is have very useful application like brain-computer interface, right? So so now we are able to maybe programming a lot of programs to help better brain-computer interfacing or do some information exchanging understanding. Okay, so to train this, they have a generator, right? So they take the EEG features or signals and have some noise, and they go through this deep convolutional network and generate an image, right? So this generator will take these EEG signals and some noise and generate the image. And the discriminator will trying to differentiate, right? Is this the corresponding image corresponding to this EEG signal, okay, the real image or the fake image, okay. And here are some of the, once the network is trained, and this is some of the output that is being produced by the generator, okay, and the input is the EEG signal. Okay, so as you can see, that is able to kind of capture some of the semantic information, right? The airplane, and this is the panda. Although it's not like it's not very realistic panda image, but have some like a concept or some of the attribute of the panda, right? You can see this black and white pattern, and those faces, right, is actually corresponding to the EEG signal generated by looking at this panda image. Okay. Okay, so of course, I mean, any AI or machine learning technique can be like double-edged sword, right? So on one hand, the scan technology is able to benefit a lot of applications we kind of briefly introduced here, right? Image generation, editing, etc. But on the other hand, it also brings some of the negative impact, right, to the society. So one particular example is called the deep fake, okay, because the GAN, the improved GAN technique is generate so realistic image, right? We can generate those fake identities or maybe do some face swapping, to generate a fake video, right? So here, actually, you can look at this deep fake. This is the actual video, right? So this is the original video, right? This actor was doing some demonstration, right? Doing some cooking demonstration, but using this deepfake technology is able to kind of swap, kind of this kind of identity from this person, right? Have some of the facial and attribute mapped to this person, right? You kind of generate a new identity, right? To which you couldn't tell the difference, right? Is this a real or fake, right? For a human eye, it's really difficult to kind of differentiate if this is a real or fake, right? There's no obvious artifacts to easily to tell this is a fake video because of the advancement of the technology, right? And you can see that that can bring a lot of harm, right? So if you generate like a video, maybe like do some face swapping, right? Maybe generate some of the fake announcement, like maybe from the president, right? You can imagine that could be leading to some catastrophic, disaster, right? Maybe the market crash, right? If you have some fake news videos by the president, bring down some bad news, right? So that could be very dangerous. So there's right now a lot of research effort has been devoted, kind of detect these deep fake, right? How can we come up with the like a digital forensic technology is able to identify if this image is going to be real or or a computer generated image or video. Okay, so there's a lot of research or interest going on, and also Facebook kind of also advocate, or I should say Meta, the company, also have this kind of deepfake competition. They have those data sets, and the teams can propose new method to evaluate or test their algorithm to see how they are able to correctly predict, right, or detect this is a fake image or video. Okay. And here are some of the reference I list here. If you are interested in to know more about the GAN for the medical image analysis, so here are actually 3 survey papers you can look into, which very comprehensive summary of different techniques, right, for different applications. And if you're interested, go check these survey papers. And also here are some of the training text, tips, how kind of good practice you can use to train your GAN model. And also there's some GitHub repo, right, to post, the latest or recent train the models, right, different GANs and the train the models. So you don't have to train from scratch. You may take some of the pre-trained GAN model and apply to your own application. So these are some very useful resources you can look into, okay? Okay, so I think that's it for today, and we kind of end a little bit early. So do you have any questions? Okay, how about questions about like the proposals, other things? If you have any questions, we can also discuss here. Okay, if not, we're gonna end here. Remember, I think the proposal due date is tomorrow, right? So please, submit the proposal on time. Okay.
Professor?
Yeah.
I was actually, it's just a request. The proposal due date is tomorrow, right? Can we have just till Friday time so that we can next Monday, so that we can at least have a weekend to look at more options, because in such a short in this period of time, due to all the assignments and all,
Yeah.
we are not getting a good look at what we really want to implement, right? Like something which is okay, fine, we can't it's our first time working with medical image computing. That's the one reason that it's taking more time.
Okay.
But if we can focus more, and I even have some questions, like how to go about it. I will mail them to you, some of my ideas. And if we can have some more time, just up till Monday.
Yeah, sure. So that's why I kind of post 2 times. So does any other student want to postpone to maybe Tuesday? I guess I can give you one more days, Monday till Tuesday night. So is there any more request on the extending the deadline?
Yeah, I would also request that deadline next week.
Okay. All right, so I'll just extend to next Tuesday, but that's gonna be the final extension I will give, because we cannot keep postpone the deadline. Otherwise, you won't have a concrete idea or starting to implement some of the project. Okay, so once you quickly settled what do you want to do, and feel free to let me know if you have any doubts, right? I'm available to discuss some of the details if you're not clear. Once you settled, then I wanted you to focus your time and energy actually doing this kind of implementation. Okay, but I think that will take most of your time. Okay.
Okay, Professor.
Okay, all right. So I'll make that extension, and you should reflect that after this class. Okay.
That's then how would we know if we are not clashing with other members in the class about the project? Multiple people can choose.
Like I said, that's okay. So if you doing the same project or topic with the other student, that's totally fine. So I already thought about that. But since you are not communicating with each other, I assuming you will have maybe different method, right? Or some of the implementation will be different. But I think the general topic can be similar, right? Because I give you the list of project to choose from, right? Maybe some of student 2 or 3 may interesting into the same topic. They may do similar, the same project. That's totally fine.
Yeah, but yeah, the project title may be the same, but the way they approach the problem should be different.
Yeah. So yeah, because you're doing this individually, right? So it's gonna be difficult. The chance everything is gonna be the same will be low, I would say. Okay.
Yeah.
Okay.
Yes.
Okay. All right.
Thank you, Professor. Thank you.
Yeah. Okay, no problem.
Production,
Yeah.
Regarding office hours, could you just at least have fixed 1 hour during the week, because as you are reading this paper assignments this about the projects, would you like to
Can
just
you,
hold a solid
yeah,
office?
can you repeat your
Solid,
question? I didn't hear you. Can you repeat your question?
yeah, sure. Can you have particular timings every week for the office hours,
Yeah.
or should we just try to mail you every time for an office, requesting an office?
Yeah, so yeah, sure, I can do that. But I think the reason in the beginning I didn't specify the office hour is, based on my previous experience, I list some time, but no one show up. So, so that's why. But yeah, if you have this request, I can definitely make the office hours. So I probably
Yeah.
Do you think maybe half hour or hour before the class will be fine? It depends.
No, after the class, or on the days where the deadlines are there.
Yeah.
That would work.
Okay. Okay. So yeah, I'll think about that then. I'll send you guys announcement, right, for the specific office hours. Okay. But if you if you need more like a time slot, based on your schedule, right? So you can let me know. We can set up individual ones. Okay.
Okay. So can we just request a discussion group for every paper in the course page? We can just start a discussions, right?
Yeah. Yeah.
Because these papers are usually contains the medical terms and medical jargons. We can form groups and try to answer each of the questions in the discussion group.
Yeah. Yeah. Sure.
Yeah. Thanks.
Okay. Okay. All right. Yeah. Go ahead.
Can we have some office hours tomorrow, if possible? So that it's my personal request, so that it's first time we are handling this, right? So if we can discuss some of the points in your office hours, it can be multiple students one by one. It would be great. We can at least have an insight about what we are working on exactly.
Yeah. Yeah, sure. So I think what I can do is I'm pretty packed tomorrow, but I think I'm available tomorrow from 10:30 to around 11:30. So for 1 hour.
That works, Professor.
Yeah, so yeah, I will send you guys announcement, right? So basically I'll just like a Zoom session. I will send out an announcement, and this is the Zoom session. So if you have any questions during that 1 hour time window, please feel free to join. So that I can help, be welcome. I'll be happy to answer your questions.
Sure, Professor. That will be great, Professor. Thank you.
Okay.
Professor, I have one question regarding the assignment, the programming assignment. So yes. Can we use either TensorFlow or PyTorch, or is it just one framework we have to use?
No, I don't specify which, one particular platform you can use. So it depends on your, proficiency, or if you prefer to using TensorFlow, you can using that. If you prefer to using PyTorch, you can using PyTorch, right? I don't have a specific preference.
Okay, and then one more question is when implementing the neural network, would it be okay if we just implemented using the library, or do we have to completely re-specify each layer?
No,
rebuild
yeah,
okay.
You don't have to implement those gradient descent, etc. So you can using the existing library, just call the function, right? Basically, you just lay the layers, then or call some of the built-in functions to implement. Okay.
Okay.
Yeah.
Thank you.
Yeah, no problem. Okay. Any other questions? Okay. Let's see. Do we have more? Okay, great. All right. Thank you, guys. You have a nice weekend as well. Okay. Bye, everyone.
Thank you.